Okay, so let's go ahead and work through example 1 together. We're going to be working with end behavior and how that relates to horizontal asymptotes today. So as it says up here, when we want to find the left and right end behavior, we need to take the limit as x goes to infinity or negative infinity. So if we imagine this function as x gets really large, as x approaches infinity, the top is going to go to infinity, but so is the bottom. The top's actually going to go to negative infinity because of the negative coefficient. The highest powered term is going to control what happens to this function, and so the negative 4x squared, as x approaches infinity or negative infinity, we're going to square it, which makes it positive, but then there's a negative 4 in front. So that's going to go toward negative infinity. The bottom is going to go toward infinity, and so we have negative infinity over infinity. Infinity is not really a number, so we can't apply properties of fractions and say that that's equal to negative 1. It's definitely not in this case. And so that's why I indicated here that there's a trick that you can use when you're trying to evaluate limits and x is going to infinity or negative infinity. What you can do is divide by the highest power of x that you see in the denominator, and that will help you evaluate this term by term. So what I'm going to do is I'm going to take every term and divide by what's the highest power of x that you see in the denominator? X to the first power, right? Okay, so I'm going to divide everything by x to the first power. As long as I'm doing that to everything, that's just like multiplying by 1. And so now I can rewrite that function, and so that is going to be negative 4x and then minus 2 plus 5 over x, and this is going to be 1 minus 4 over x. Okay, now imagine plugging in a really large number, like 1,000, let's say. If we plug in 1,000 or 10,000 or 1,000,000, what's going to happen to this term? Say that louder, Brandon.
It's going to get smaller.
It's going to get smaller. It's going to approach 0. So anything that still has an x in the bottom is going to approach 0. That's going to approach 0. And then the 2, that's just a number, and the 1 is just a number. But the negative 4x, that's going to get larger and larger and larger. And so as x approaches infinity, sorry, I'm just trying to insert some space here. So as x approaches infinity, notice that this is going to get really, really large, but the denominator now is only approaching 1, because it's 1 minus 0, which is 1. So the top's approaching negative infinity, and the bottom's approaching 1, so we can say f of x approaches negative infinity. So that gives us our right end behavior. So that tells us that as x goes to the right, the y value is going to go down. So this graph is going to finish going down for sure. Okay? And then as x approaches negative infinity, what's happening to f of x? If you plug in a really large negative number like negative 10,000, we're going to have negative 4 times negative 10,000, which is positive 40,000. So this is going to get really, really large. Okay, the bottom is still approaching 1, and so now in this case it's approaching infinity. So that means as we go to the left, this graph goes up. So we're not talking about what's happening in the middle of the function. We're just saying that as this graph goes far to the left, it's going to go up, and as the graph goes far to the right, it's going to go down. So that's called end behavior. Okay? And so this is the conclusion we're looking at. We're just trying to decide what's happening to this graph as we go far to the right and far to the left. Okay, so the formal mathematical way to write this out, when I said we're letting x approach a really, really large number, when we do the the right-hand behavior, we're looking at the limit as x approaches infinity of negative 4x squared minus 2x plus 5 and x minus 4 in the bottom. And so we said that that limit is equal to negative infinity. That was from here. And then the limit as x approaches negative infinity of negative 4x squared minus 2x plus 5 over x minus 4 equals positive infinity. Okay, so the LIM, that is just an abbreviation for limit. I think this is probably the first time a lot of you have seen a mathematical limit. But what that means is we're just, as x approaches infinity, we're just letting x approach a really, really large number and a really large positive number, and then as x approaches negative infinity, a really large negative number. And so that's all that LIM means. We're just taking the limit. We're letting x get as large as it possibly can. Okay? So let's go ahead and look at what happens on example 2. It's going to, if you read the problem there, you can tell already that something else is going to happen. Instead of approaching negative infinity or infinity, in this case it's going to approach a number. So copy that one down and then see if you can apply the limits like we did in problem 1 and see what the limit equals. Okay, so what did you all get for the limits, the left and right end behavior limits? You got 2? Anyone else get 2?
I got 2.
You got 2? Okay, they should be 2. If we look at the limit as x approaches infinity of 4x squared minus 2x plus 5 over 2x squared minus 4, the highest power of x that I see in the denominator is x to the second power. So I'm going to divide everything by x to the second power. And so x squared, x squared, x squared, x squared, x squared. Now when I simplify that, this becomes the limit as x approaches infinity of 4 minus 2 over x plus 5 over x squared divided by 2 minus 4 over x squared. Now remember, anytime there's an x in the denominator, if x is getting really large, that's going to make that fraction approach 0. So this has an x in the denominator that's going to infinity, so that's going to approach 0. This fraction is going to approach 0. This fraction is going to approach 0. So all we're left with is 4 over 2, which is 2. So those of you that got 2, you did that correctly. Okay. Also, if I change this to x approaches negative infinity, nothing's going to change here. It's still going to just approach 2. And so you might be wondering, what does that mean that the function is approaching 2 as we go to the left and the right? So I could write the statement as x approaches infinity, f of x approaches 2, and as x approaches negative infinity, f of x approaches 2. So that describes the end behavior, but what does that mean graphically? And so I asked you to graph it on Desmos or your graphing calculator. If I graph it on Desmos, what do you notice? Okay.
It intersects at two points.
What intersects what?
The graph, it intersects at 2 and it keeps going.
At what? At x equals 2, y equals 2? What are you saying?
When I'm just saying that the graph would intersect. Yeah, y is equal to 2.
So I'm looking at y equals 2, and I don't see the graph crossing the y-axis at y equals 2. Gianna?
2 is the horizontal asymptote.
That's right. If I graph y equals 2 as another equation, y equals 2, do you see the blue line? the red curve is getting closer and closer to that blue line. So when we analyze end behavior and we get a number instead of infinity or negative infinity, that means the graph, as we go far to the right and far to the left, is approaching the horizontal line y equals 2. Okay? So that's, and then if we look at it on the graphing calculator, we see exactly the same thing. If I graph a function y equals 2, we can see that the curve is getting closer and closer to that horizontal red line as we go further to the right and further to the left. And so that's what we should write here with this problem. Say this graph, or this function, has a horizontal asymptote at y equals 2. Okay? So that's what it means. My original question was, what happens to the end behavior when the limit equals a number? What happens is you get a horizontal asymptote.
Mr. Dixon?
Yes.
On the Desmos graph, like, the, it, like, crosses the blue line, though.
Yeah, if you look, there's a point there at 6.5. At x is equal to 6.5.
Okay, that's a good thing to notice, but there's nothing wrong. There's nothing that says a graph cannot cross its asymptote. What it means when we say that a line is an asymptote, that means it's going to get closer and closer to it as we go further to the right and further to the left. So you're right. Look at this. The red curve is above the blue line, and then it's below. But still, as I go further and further to the right, do you see? It's underneath, but it's getting closer and closer and closer. So I'd have to really zoom in to see the difference between those. And as I keep going to the right, it just keeps getting closer and closer and closer to the blue line. Okay? So a lot of people have the misconception that they think a curve can't cross an asymptote. An asymptote's not a line that your graph doesn't cross. An asymptote is just a line that your graph gets closer to as we go to the extreme right or left, or if it's a vertical asymptote, then it'd be going that way. I'm having to go forever to get back to the original graph here. But anyway, there we see that intersection that Vi and Vincent were talking about. Over on this side, it never does cross, but it does continue to get closer and closer and closer to that asymptote as we go further away. Okay? And on the graphing calculator, you could also analyze that with a table. So you could be looking at the values in the table and what happens as they get bigger, as they go closer to infinity or negative infinity. On both, you're going to get the same result, that as we go further to the right and further to the left, they get closer and closer to 2. Okay? All right. So now, go ahead and use what you just learned to find out if these graphs have any horizontal asymptotes. Okay, so let's check in and see how you're doing here. In the first one, the highest power of x in the denominator, again, is x squared. So I divided everything by x squared. And when I did that, all of the fractions, all the fractions that had still an x remaining in the denominator are approaching 0. And so the entire numerator is approaching 0. So I'm looking right here. This entire numerator is approaching 0. And the entire denominator is approaching 5 because it's 5 minus 0. And so 0 divided by 5 is 0. Now take a look. If I had changed the infinity to negative infinity, would anything in this problem change? No? all the things that are approaching 0 are still going to approach 0 when x approaches negative infinity, and so we still end up with 0 over 5. And so the left and the right end behavior for both of those is 0, so what does that mean? Horizontal asymptote where? Y equals 0, which is really the x-axis. Okay, so f of x has a horizontal asymptote at y equals 0. Okay, that's the x-axis. Okay, and then part B, we do the same thing, divide everything by x squared because that's the highest power of x that I see in the denominator. And I end up with a 3 in the top and a negative 4 in the bottom. Everything else is approaching 0. So as x approaches infinity, I just get negative 3/4. The limit is equal to negative 3/4. And again, it doesn't matter if I let x approach infinity or negative infinity. So I'm going to say plus and minus infinity for both part A and B. And so our end behavior, the graph is approaching negative 3/4, so f of x has, again, a horizontal asymptote at y equals negative 3/4. Any questions? Okay, so I just kind of summarized what we just did in this next paragraph, so you're welcome to copy that down if you think that's helpful. Okay, so I also want to go back and look at these examples again and see if we can recognize a pattern with the degrees of the numerator and denominator. So look at our very first example today. The degree of the top was greater than the degree of the bottom. Okay, we had an x squared in the top and an x in the bottom. That gave us end behavior where there was no horizontal asymptotes. So at the ends, it was going to approach infinity or negative infinity.
Doesn't that mean that there's like a slant asymptote?
If there's 1 degree of difference between the two, that is true. That's what we're going to talk about tomorrow. So in this case, yes, there is 1 degree of difference between the top and the bottom. And so that does give us a slant asymptote. So that's what we're going to talk about tomorrow.
Does it matter which way the difference is?
Yes, when the degree of the top is 1 greater than the degree of the bottom, that's when you get a slant asymptote. Okay? All right, in the second example, the degrees were the same, and what ended up happening? There was a horizontal asymptote, and do you recognize a pattern of the number that we got? Look at the original function. How could we have gotten the 2 more quickly? Yeah, just look at the highest powered term in the top divided by the highest powered term in the bottom. 4x squared divided by 2x squared is just 2. Okay? And then in example 3a, this is the first one where we've seen that the degree of the bottom was greater. And what happened when the degree of the bottom was greater?
0.
We still got a horizontal asymptote, but it was at 0. Okay? And then in example B, again, they're the same power, and so we could have just analyzed the first term in the top over the first term in the bottom, and that would have given us negative 3/4. Okay? So I have here the shortcut kind of in a little table. The first column is telling you the degree of the numerator and the denominator. If the degrees are equal, then we have a horizontal asymptote at y equals the ratio of the coefficients. That shouldn't say example 1, that should say example 2. When the denominator has a greater degree than the numerator, we get y equals 0 as a horizontal asymptote, just like we did in example 3a. And if the denominator is has a lower degree than the numerator, that's like example 1 today. See example 1. Okay? Then we get no horizontal asymptote. Okay? And that is it for today's lesson. We'll continue with more tomorrow. And so I have some problems I selected from this section for you to work on. Only those problems, so we're not doing them sequentially like we normally do. Sure.
Can you go back to the home?
I can't be on both at the same time.